Okay, today what I'm going to be doing is I'm going to be walking through the notes on tides, parts of a wave, and ocean currents. All these notes are going to go on the ocean currents note sheet. The information about tides and parts of a wave can go on the back of the paper where it's blank, or you can certainly do it on a piece of lined notebook paper if you would prefer. So I'm just going to talk about tides. I know you've watched videos on Edpuzzle and you've learned a lot about tides. So I just want to make sure we're all using the same language and we don't have any misconceptions as we move forward before we take our next test. So a tide is the rise and fall of sea level that's caused by the pull of the moon. When that sea level rises, that's a high tide, and when it falls, it's a low tide. High tide occurs as a bulge of water where the moon is in its orbit and on the opposite side, and we'll look at this in an illustration in just a moment. And spring tide is when the tides are higher and lower than their normally during a tide due to the sun being lined up with the moon's orbit. And so we have the gravitational pull from both the sun and the moon, making those tides more extreme than they normally would be. And then a neap tide is when the tides are lower than normal and the low tides are higher than normal, and it's because the pull is divided between the sun and the moon. So this happens when the sun and the moon are 90 degrees at an angle from each other, and we'll look at that in just a moment. So if we look at this picture, when the Earth and the moon are in their orbits, and we know that the moon orbits the Earth and then the Earth orbits the sun. So one misconception, and I apologize if I made this misconception because I think I might have, is that the moon travels around Earth once every day, and that's incorrect. It takes the moon 27 days to travel all the way around Earth's orbit. But the Earth is rotating on its axis, and so it rotates around once every 24 hours. So in a day, we have 2 high tides and we have 2 low tides. The tide is based on where it is in relation to the moon. So when that coastline is facing the moon, it's going to have high tide. Same thing when it's directly across from that side of the moon. And then when it is perpendicular to where the moon is in its orbit, there's going to be a low tide. Okay. When we have that spring tide where they're more extreme, what we'd have is we could have the sun here, Earth, and then the moon, or we could have the sun, the moon, and then the Earth. And when they're all lined up, there's a lot of pull, and that's why the high tides are higher than they normally are, and low tides are lower than they normally are because of all that gravitational pull. The neap tide, we'd have the moon here and the sun would be up here or down here in its orbit. And so the moon is pulling as well as the sun, and that's why the high tides aren't as high as they normally are, and the low tides are higher than they normally would be, meaning they're not as low, because there's 2 different things that are pulling on that with gravity on Earth's oceans. All right, so next is parts of a wave. Before you write this down, you just might want to do a diagram. There's only 4 pieces you need to know. You do not need to know wave frequency and wave period. If you go on and take physical science or physics, you will get those topics. But what you have are, you need to know these 4 parts of a wave. They are parts you should have learned back in middle school, so this should be review. So this is our wave. The top of a wave is a crest. The bottom of a wave is a trough. We usually draw this midline kind of right in the center. And then the distance from that midline to the crest or midline down to the trough is called the wave height. And a wavelength is the distance from crest to crest or trough to trough. Okay, once you have those labeled and your tides notes done, you can flip your sheet over and we're going to do ocean currents. So with this, I'm going to read through the slide and then I'll help you with what you need to write down on your sheet to answer the question. So we're going to look at ocean currents. These are some of the major currents, not all of them. We're going to look at the effects of wind, the Coriolis effect, density, and geography on ocean circulation patterns. So surface currents, these are the ocean surface currents that occur in patterns. You're going to notice they're colored for warm currents, cold currents, and the black ones are ones that we don't worry about if they're warm or cold. We think about warm and cold when we have a current that's coming up along a coast because it affects weather. And we'll look at that in a little bit. Therefore, direction and temperature of the currents tend to be predictable. Prevailing winds, the sun's uneven heating of Earth, the geography of the land, and the rotation of Earth all play a role in surface currents behavior. So your first question, number 1, says ocean currents are a result of several influences. These are, and they're these right here. So it would be, I'm just going to grab a pen, it would be prevailing winds, sun's uneven heating of Earth, geography of the land, and rotation of Earth. Those are the 4 things that play a role in the behavior of those currents. Okay. All right. I'm going to try to move on to our next slide here. All right. So then it says the Earth turns. The Earth is heated unevenly, and it's warmer at the equator and colder at the poles. We know that. You learned that back in elementary school. And in this picture, they have the Earth straight up and down. We know that the Earth is at an angle, and that's how we get seasons. For example, here in the northern hemisphere, when we are tilted away from the sun, it's when we're in winter, and when we're tilted towards is when it's summer. So the seasons are opposite in the southern hemisphere. When we have winter, they're in summer. When we're in summer, they're in winter. So the warm air that's at that equator, it rises. We talked about convection currents earlier when we were looking at below the Earth's crust. Same thing happens with this air. So it's cold at the poles, it comes down towards the equator and it gets heated up, and that heated air rises. And so it essentially makes this big circle. Okay. This airflow would normally travel in a straight line. That's what they're representing with this dotted line here. But since the Earth rotates, it has a curved path. It's deflected. So on your sheet for number 2, it says, how does Earth's rotation affect the distribution of airflow? You can write that it is deflected. Okay. All right, convection currents. So this uneven heating from the sun creates convection currents in the atmosphere, and that's what creates the winds that we feel. The air is heated at the surface, and more so near the equator. That heated air rises, cools, and sinks to be heated again. And these convection currents are seen in the diagram along with the major wind belts. So at the equator, we have these trade winds. We have westerlies in the middle, and then the polar easterlies, and it's the same in both hemispheres. The major wind belts are given names according to the direction from which they originate. So if they are coming from the west, they're the westerlies, even though they blow east, and the polar easterlies are easterlies because that's where they're coming from, even though they blow to the west. The question on your sheet that it asks about is, what are convection currents? That's number 3. So you can write that convection currents are what create the winds, and it's from uneven heating from the sun. And then that would be question number 3. And then question number 4 is answered down here. It says, how are the wind belts named? They're named from the direction from which they originate. Okay. All right. Then the doldrums and the horse latitudes. Okay. So between the belts are latitudes where there's very little air movement. This is where the air is either sinking or rising. And so we have 2 special ones along the equator. Since the air is rising, there isn't a lot of wind. And so this is called the doldrums. And I think it's named from sailors in the early days of exploration. Since there was very little wind, they didn't move very fast. The trip got very boring and dull. And so it's become known as the doldrums. At 30 degrees north and south latitudes, the air is sinking, and again, very little wind. These are called the horse latitudes, and they think that the early sailors that got caught here where there was very little wind thought that if they threw a horse or several overboard, it would lighten their load. They'd have less mass that they were carrying on their ship, and they could travel a bit faster, and so these areas became known as the horse latitudes. So on your sheet, we are answering question number 5. Hot air is rising at the equator. Number 6, the doldrums are at the equator. And number 7, around 30 degrees latitude, is the horse latitudes. All right, next we're going to talk about the Coriolis effect. The Coriolis effect is really because we rotate on our axis, we don't get these nice perfect circles of air rising and sinking as it cools. Instead, we get these deflected winds because of the Earth's rotation. And so the prevailing wind patterns are seen to the right. This would be what it would be like if we didn't have rotation. This is what it actually is like because of that rotation, which we call the Coriolis effect, is that deflection of the wind. In the northern hemisphere, winds are deflected to the right in a clockwise rotation, and in the southern hemisphere, they're deflected to the left in a counterclockwise direction. So on our sheet, the Coriolis effect, number 8, is you can just write that it is the deflection of winds. And then for number 9, winds in the northern hemisphere are deflected to the right. Okay. All right. How does this affect the currents? Surface winds across a large body of water like the ocean will cause the surface of the water to move in the same direction as the wind. And so in addition to the winds across the surface, the rotation also affects the ocean currents. And so they're going to move similar to the wind. The ocean currents will. So in the northern hemisphere, they curve in a clockwise pattern. In the southern hemisphere, it's counterclockwise, or the opposite of clockwise. Okay, on your sheet, this is question number 10. It says, explain the Coriolis effect on ocean currents. You can say that the surface of the water moves in the same direction as the wind. And then I would write that in the northern hemisphere, they curve in a clockwise direction. Southern hemisphere, counterclockwise. All right, the effect of geography on the currents. The geography of the planet affects currents as well. When the flowing water encounters a continent, it's deflected. And so the flow becomes a circular pattern, and these huge circular currents are called gyres. So there's that clockwise and counterclockwise. We call these big circular patterns gyres. So on your sheet, we're answering question number 11. What is a gyre and why do they form? A gyre is a huge circular current, and they're formed because the current hits the shoreline, or you can say it hits land. All right, and then upwelling. This is an interesting thing that happens. So upwelling is when water from deep below the surface is drawn up to the surface because of the movement of the surface currents. So as the wind blows and we get these surface currents of water, those surface currents help to create the deep water to upwell or come up. And happens at the equator. It can also happen at shorelines. And this upwelling brings nutrient-rich water to the surface where it becomes accessible to organisms living in the photic zone. So what does that mean? We have nutrients down at this bottom, and there aren't a lot of organisms that live down in this dark, cold water. Most organisms live up in what they call the photic zone, or the area where the light comes through the water. And so the upwelling brings these nutrients up for more organisms to have access to them. So on your sheet it says, how does upwelling occur? And you can say that it's when water from below is drawn up to the surface. Okay? And it's important for ocean life because it brings nutrient-rich water to the surface. Okay, I'm going to stop the video here. This is the end of part 1. The rest of this will be answered in part 2.